Okay, welcome back. In this video, we're going to once again be looking at an ideal gas, similar to the last video, but it'll be a little more quantitative in nature. That being said, go ahead and take a look at the problem statement. So in this problem, we have 2 moles of an ideal gas that's taken through a continuing cycle. It starts out with a heating at constant volume, then there's an adiabatic expansion in which its volume doubles. Next, it's cooled down at constant volume, and then it goes through an isothermal compression back to its original state. We're told a little bit about the heat exchanges and temperature changes during this process, and we're asked to find a few things, including how much heat is exchanged during the isothermal compression, and then what type of gas it is, and then finally, what is the max temperature during the entire cycle. So to start out, it's not giving us a PV diagram at all, so it might be useful to kind of visualize what's happening in terms of pressure and volume changes during the cycle. So let's go ahead and have you guys draw a PV diagram and just label each of these maybe as the points in between them as A, B, C, or D. And we'll come back and just take a look at that. And from there, we'll make a table of the work, heat, and energy exchanges as we did in the previous problems. So go ahead and take a minute now, draw a PV diagram, and we'll come back and take a look. All right, so taking this piece by piece, let's start with the heating of the sample at constant volume. Constant volume means it's got to be some sort of vertical line for that portion. Now, is it moving upward or downward? Well, we know that it's heating up, so temperature should be increasing. And we know that isotherms have a 1 over x type of shape to them. So in other words, an isotherm meaning that anywhere along this curve will be the same temperature. And these isotherms increase in temperature as you move outward in that direction. So this will be a certain temperature, this will be a higher temperatures, etc. So to go from a lower temperature to a higher temperature, you've got to move upward. So this is going to be a vertical line that just basically moves upward. So I'll draw it like this. Okay, so this is step 1. Now step 2 is an adiabatic expansion in which the volume doubles. So you know you're going to get to double the volume. And we know that adiabatic expansions look similar to isotherms, but they're a little steeper. So an isotherm may look like this. Adiabatic will be a little steeper, but it also kind of goes down. So I'll draw that one going down. Okay. And it's not really to scale. It should double the volume, but you get the idea. Now for the second part, we're going to cool it down at constant volume. So it's going to be a vertical line again, but now it's going to go downward. Okay. And then the last part is going to be an isothermal compression. So now we've got to be moving along an isotherm. So you've got to be moving somewhat in this direction. And again, because adiabatic paths are generally steeper than isotherms, I'm going to kind of draw it a little less steep. So it'll look like this. Okay. And so this is moving in this type of direction. Let's label the parts we started here, so I'm going to label that as A, and then just continue around. So I'll call that A, B, C, D. And I've also made a table over here in which we're going to tabulate all the heat exchanges, the work that's being done, and the changes in internal energy along each of these paths. So as we've done in the last few videos, you want to start filling in whatever you know based on a couple of kind of implicit information given in the problem. In other words, if it's isothermal, it might tell me something about either one of these quantities. If it's adiabatic, the fact that it's cooling at a constant volume or something like that. It may tell you some values to put in here, so go ahead and fill in whatever you know just from the information given, and then we'll come back and proceed from there. So the first thing you want to fill in any of these charts is the total internal energy change along any full cycle has to be 0. And it's got to get back to where it started in terms of internal energy. Now, let's use some other information. Well, we have the adiabatic expansion. Adiabatic, by definition, means that no heat is exchanged with the environment. So for the adiabatic expansion, part BC, we have a total heat of 0. What else? Well, we have constant volume processes. The work done depends on how much the volume changes. If the volume is constant, there's no work being done. So along CD and AB, we have 0 work being done. And then finally, we also have the heat here is 4135 given in the constant volume cooling. So in CD, we have heat being taken out of the sample because it's cooling down. And that's CD, so we have minus 4135. Using the first law of thermodynamics, this row minus this row must equal that one. So this minus this must equal the total internal energy change. Okay, so we have that. And then there's one last thing we can use, which is for an isothermal compression. In ideal gases, the internal energy change is proportional to the temperature change. So for an ideal gas, you actually have delta E is proportional to delta T. And this is something that at this point we don't know, but we know that if it's isothermal, the change in temperature is 0, so the change in internal energy has to be 0 too. And that's for the isothermal part, which is BC. So we know we have, which is dA. So over here we have a total internal energy change of 0. And that's all we can get out of the information given. Now we want to first find out, the question's asking us to first find what is the amount of heat that is exchanged during the isothermal compression. That is leg dA. So we're looking for this quantity right here. If we had the work done, we could find that by subtraction. We can't find the work done. So let's go ahead and write down an equation for the work. For any gas, the work done is always going to be this formula. Okay. Now for an ideal gas, we have PV equals nRT. This is why the ideal gas part helps us out, because we have some extra information. For the ideal gas, we can plug this in here. Notice here in this integral we have two variables, so we can't integrate yet. However, we can get rid of the p in favor of v by solving this for p. So p equals nRT over v, plugging that in. We get nRT over v. And the reason this is useful for an isothermal process is during an isothermal process, T is constant. You can take out the entire numerator out of this integral. So then all you have left is the integral of dV over V. Okay, for an isothermal process, that's possible. For other processes, this is changing in time, so you can't do that. Integrating this, you get the natural log of V, and so when you plug in the endpoints, you simply get nRT times the natural log of the fractions of how the volumes have changed. Okay, and actually, we know everything here. We know that there's 2 moles, the gas constant is constant, the temperature change along this isothermal process. We know it cools down from 300 to 200, so this is all 200 degrees. So we know the temperature. And then the volume, how much does the volume change? Well, we know that it doubles from B to C, so the volume must half from D to A. Right? So this VF is going to be 1/2 of VI. VI is canceled, you just get 1/2 here. So plugging in all those values, you'll find that the total amount of work done is minus 5,449 joules. Now be careful here, when you plug in temperature, it's got to be in Kelvin. When you subtract temperatures, you can use Celsius or Kelvin, but if it's a temperature by itself, it's got to be in Kelvin. All right, so we can plug that in over here. That's for the work done. And then since this quantity minus that's got to be 0, they have to be the same. So the work done in the isothermal process is this. That tells us the heat exchanged is minus 5,449, and it's got to be taken out of the sample because it's negative. So in dA, leg dA, we have this amount of heat being taken out. Okay. You see how the table has really helped us to organize our information and find that quite easily. Next question says, what kind of gas is it? Is it monoatomic, diatomic, or polyatomic? How is that related to anything we have in the problem? Well, this depends, or this dictates what the heat capacity is. So if we have the heat capacity, we can work backwards to find the number of degrees of freedom, and based on that number, we can find out what kind of gas it is. So what we want to do is find the heat capacity. You see that heat capacity enters this formula for the internal energy. So we want to be using something about the internal energy. And notice we have here, well, we have that along the entire cycle, the internal energy change has to be 0. So this plus this plus this plus this has got to be 0. What we can do is the following. We can plug in this formula for these both, and we know some temperature changes, so maybe we can plug in some known temperature changes for this part, and hopefully solve for the heat capacity, which is the only remaining quantity. So go ahead and do that on your own. Plug this in for these guys, and try to invert the equation to solve for the heat capacity, and from there we'll find the degrees of freedom, and then characterize the gas. So go ahead and take a minute to do that now, and we'll come back and take a look. So using the energy changes along the entire cycle have to add up to 0. We can write this as the energy change along AB plus that along BC plus that along CD, which is minus 4135, plus 0 must equal 0. Right? And we're going to use this equation, which is true for any ideal gas, to rewrite this in terms of heat capacity and temperature changes. The temperature change between A and B, I'll just write as TB minus TA. And then likewise for the next leg. If you look at this carefully, you'll see that the TB terms will cancel. So we just have the temperature at TA and TC. The temperature at TC we know is at 300 degrees. The temperature at TA, since this is an isotherm, everything along this has to be at the same temperature. We know it goes from 200 to 300 here. So this is 300. Anywhere along this is 300, so TA is 300. This is 200. So this is 200, and this is 300. So we can we know those values here, TC and TA. We can plug those in. We know N is 2, and we know this guy, so we can just solve for CV. So, and this is all in detail in the write-up. You'll find that CV, given those temperatures, equals 20.675 joules per mole per Kelvin. Now, given the heat capacity, we can immediately get the number of degrees of freedom. So for an ideal gas, the heat capacity depends on the number of degrees of freedom in the following way. The number of degrees of freedom divided by 2 times the gas constant gives you the heat capacity. So we can just invert this equation to solve for F, and using our value for the heat capacity, we'll find that the number of degrees of freedom, what we get for this is 4.97. Okay, well, this is very close to 5. And that tells us that this is a diatomic gas. Diatomic gases have 5 degrees of freedom, whereas monoatomic gases have 3, and then polyatomic have 6. So this is more of like an experimental procedure. What would actually happen in a lab is you can measure heat exchanges, and you can keep things at constant volumes, or you can change the volumes as you wish. Using that information, you can go back and infer what this F value is, and then you can find out, well, it's very close to 5, so it's probably a diatomic gas that makes up my sample. So for example, you might have a gas made up of hydrogen 2 or oxygen, which are both diatomic gases. Okay, so this is diatomic. The last part of the problem asks us to find the maximum temperature of the entire cycle. Where does that occur on here? Well, this is at 200 degrees, C is at 300, and this is not isothermal. This actually drops temperature because an isotherm is going to be at a more gradual slope here. So this is at a particular temperature, whereas B is above that. So the highest point on this entire cycle is going to occur at a temperature of TB. So the max temperature occurs at T sub B. So we got to find the temperature at T sub B. Now, how do we proceed? What we can do is use the fact that, well, we don't really know what's happening on A, B. We don't have any heat exchanges here. It's kind of missing. We do know that this is adiabatic, though. For adiabatic processes of ideal gases, you have the following conserved quantity. PV, or V is to the gamma power, is constant. Or you can rewrite this using the ideal gas law as TV to the gamma minus 1 equals constant, where gamma is the ratio of the heat capacities. And we have the heat capacity at constant volume. We just found it. And the heat capacity at constant pressure is just that guy plus R. So you can find Cp from which you can find gamma. So we do know gamma. And we want to use one of these equations because we know the temperature here. So if we know the temperature here, then we can maybe go back and find the temperature here by using the fact that this quantity is constant, and by using the fact that the volume has doubled between here and here. So this equation will be very relevant. So let's use the second one, and I'll write this as, if this is constant, then whatever it is at B, which is TB, VB to the gamma minus 1, equals whatever that same quantity is at point C. This is the beauty of conserved quantities, is once you know them at one point, you know them everywhere. Now, we know TC, we know how the volume changes, we can find gamma using this value. So we should be able to find TB in theory from this. So I want to have you guys do that on your own. Invert this equation and solve for the temperature at TB, which is the max temperature of our cycle, and we'll finish up. We can use the fact that the volume doubles between B and C to write this as 2 times VB. The VB terms will cancel, so you'll end up with this following formula. You just have a 2 to the gamma minus 1. Okay, and we know Tc, we know it in Kelvin, we know it in Celsius, we can convert to Kelvin. And then from there we can plug in that with the gamma minus 1 factor. Well, what is gamma? We need gamma. Gamma is, it's defined as Cp over Cv. We know Cv, let's see, we have C sub V is F over 2 times R. F is 5, so it's 5 halves times R. The constant pressure heat capacity is always a constant volume heat capacity plus R. So it's going to be 5 halves R plus R, which is 7 halves R. 7 halves divided by 5 halves is 7 fifths. Okay. And then so in this factor, we're going to have 7/5 minus 1, which is 2/5. So all we get is TB is this given temperature times 2 to the 2/5. Plugging all those values in, you'll find that the temperature is 483 degrees Celsius. Keep in mind when you do this, though, you have to work in Kelvin because nothing is being subtracted here. So plug in the value in Kelvin and then convert at the end to Celsius if you'd like. Let's just make sure this makes sense. Right here, the temperature is about 200 degrees Celsius. At C, it's 300 degrees Celsius. And because the isotherm is below it, this has to be higher. 483 is a reasonable number. Now, I didn't ask in this problem to fill in anything else in this table. But in fact, you have enough information to fill in all the other portions. So why don't I encourage you to do that. And if you want to just check your answer, in the write-up, the solution to this, the entire filled-in table is given. So you can check your answer with that. But for now, I'm going to stop, and I want you guys to go ahead and take a look at the summary, just rehash what we did, and we'll see you next time.